So, a pleasant day, everyone. I am JUL-ARSER from BS Ed Sciences 3A. And today we are going to talk about the observation outside the Earth's atmosphere. So, have you ever wondered how it's look like? What we see from the sky above, really like what we perceive. It is beyond what our naked eye can see. Or what devices did they use to discover the mystery outside their atmosphere? But first, before that, here are our objectives for today's discussion. First is list the advantages of making astronomical observation from space. Explain the importance of the Hubble Space Telescope. And for the last one is describe some of the major space-based observatories astronomers use. So Earth's atmosphere is leaking. Every day, around 90 tons of material escapes from our planet's upper atmosphere and streams into space. Although missions such as ESA's cluster fleet have long been investigating this leakage, these are still many open questions. So how and why the Earth is losing its atmosphere, and how is this relevant in our hunt for life elsewhere in the universe? So water vapor, the main source of atmospheric interference for making infrared observations, is concentrated in the lower part of the Earth's atmosphere. So for this reason, it was natural for astronomers to investigate the possibility of observing infrared waves from airplanes and ultimately from space. So getting even higher and making observations from space itself have important advantages for infrared astronomy. First is the elimination of all interference from the atmosphere. Equally important is the most opportunity to cool the entire optical system of the instrument in order to nearly eliminate infrared radiation from the telescope itself. So if we try to cool a telescope within the atmosphere, it would quickly become coated with condensing water vapor and other gases, also making it useless. So only in the vacuum of the space can optical elements be cooled to hundreds of degrees below freezing and still remain operational. Now, what is the Stratospheric Observatory for Infrared Astronomy, or SOFIA, can do in observing outside the Earth's atmosphere, especially for the aspiring astronomers? So, the Stratospheric Observatory for Infrared Astronomy, or SOFIA, is a 2.5 meter or equivalent to 100-inch telescope carried aboard a modified Boeing of 747 SP airplane. So the airplane can fly at an altitude of 12 kilometers or 7 miles or more above 99% of Earth's atmospheric water vapor. This allows Sophia to make observation in infrared wavelengths that are absorbed by the atmosphere at lower altitudes. So, Sophia can carry scientists, crew, educators, and students in the pressurized cabin where the telescopes is controlled. So interesting, isn't it? So would you like to have this kind of experiences? So let's go to the next slide. Now let's talk about the Infrared Astronomical Satellite, or ERAS. So ERAS was the first space telescope to study the sky in infrared light. Many infrared wavelengths are blocked by Earth's atmosphere and therefore cannot be observed from the ground. So the ERAS mission showed that the universe is rich in sources emitting those infrared wavelengths. So ERAS detected about 350,000 infrared sources, increasing the total number of cataloged astronomical sources by about 70%. So the mission made a number of unexpected discoveries, including the six new comets, evidence of dust grains around the stars Vega and Fomalhaut, which strongly suggested that the existence of planetary system around other stars. Now, because infrared light can penetrate dust and gas, even when visible light or the kind of human eyes can detect, cannot. So, ERAS probe deeper into the core of our galaxy, the Milky Way, than any previous observatory. The Spitzer Space Telescope, launched in 2003, was NASA's infrared great observatory. Among many other accomplishments in its 16 years of operation, Spitzer discovered a giant ring of Saturn, revealed a system of 7 Earth-sized planets around a star 40 light years away, and studied the most distant known galaxies. So, infrared light can, and in most cases, penetrate gas and dust clouds better than visible light. As a result, Spitzer has provided unprecedented views into regions where the stars are born. So, as you can see, this image from Spitzer's shows newborn stars peeking out from beneath their natal blanket of dust and row of Yochi dark cloud. So, these infrared images, first is the Flame Nebula, Cassiopeia A, and Helix Nebula are just one of the few regions of stars formation, the remnant of an exploded star, and a region where an old star is losing its outer shell. So just a few of the observations made and transmitted back to the Earth from the SST. So the colors in this image have been selected by astronomers to highlight details like the composition or temperature in these regions. So, can you just imagine, class, no? If these things were not invented, we won't be able to see how beautiful and fascinating the things that can be seen outside our atmosphere. Let's go to the Hubble Space Telescope. So, the Hubble Space Telescope is the first in a series of orbital telescopes to study the evolution of the universe. The telescope's wide-field planetary camera has continually provided new information on the planets, including the seasonal surface variations on Mars. So, clouds and storms on Jupiter, Saturn, and Neptune, and clearer views of distant Pluto and Charon than ever before. Hubble also enabled unique views of impact of comet Shoemaker-Levy 9 into Jupiter in 1994 and provided evidence for the other planetary systems in the universe. With the Hubble, astronomers have obtained some of the most detailed images of astronomical objects from the solar system outward the most distant galaxies. So, among its great achievement is the Hubble Ultra Deep Field, an image of a small region of the sky observed for almost 100 hours. It contains views about 10,000 galaxies, some of which formed when the universe was just a few percent of its current age. Now, let's go to the next slide. Many important events in the history of astronomy, particularly high-energy astronomy, X-ray astronomy, ultraviolet, X-ray, and direct gamma ray, high-energy electromagnetic wave, observations can be made only from space. Such observatories first became possible in 1946 with V2 rockets captured from Germany after the World War II. The U.S. Naval Research Laboratory instruments on these rockets for a series of pioneering flights used initially to detect ultraviolet radiation from the sun. Since then, many other rockets have been launched to make the X-ray and ultraviolet observation of the sun and later of the other celestial objects. So those energetic particles hit other particles in the atmosphere and give off their own radiation. Astronomy and cosmic ray astronomy with particular emphasis on events concerning space-based observatories with X-ray and gamma ray detectors on board which observe cosmic. Gamma ray detections can also be made from the Earth's surface by using the atmosphere as the primary detector. When gamma ray hits our atmosphere, it accelerates charged particles, mostly electron, in the atmosphere. Like X-ray detection, gamma ray detection is done by photon by photon. So gamma rays are detected by observing the effects they have on matter. A gamma ray can collide with an electron and bounce off it like a billiard ball, or it is called the Compton scatter. Or it can push an electron to a higher energy level, the photoelectric ionization. So for the last slide, so these are the list of some of the most important active space observations that humanity has launched. Okay, that's all. Thank you for listening.